actually perturb the absorption of my photon. Okay, so this interference, because they are both sort of electronic wave phenomena, right? Your photon is electromagnetic waves. Your photoelectron is electromagnetic wave, right? So both of them can then interact with each other, interfere with each other, and therefore the interference of this scattered photoelectron wave will affect your incoming photon waves, right? Photon electromagnetic waves. And it is this interference that generates the so-called exact effect, fine structure effects. Okay? So here I say, suppose you have photon energy sufficiently high, and it causes ionization of core shell electron, and the photoelectron emit a photon wave from this emitter atom, and then it in turn causes interference. And this interference is contain information. How the wave backscatter from its neighbor is important because it contains information of the location of this neighbor, how strong a scalar is its neighbor, right? If you have something that has a lot of electrons, it will scatter the wave better than a carbon atom, for example, with not so much electron. If you have metal, it will scatter better than carbon, for example. Then consequently, for this interference modulate or change the absorption profile, absorption coefficient of the radiation. So what do you see? If you see a absorption, right? So what am I doing? I'm doing photon in, photon out. Okay, so this is I naught. Okay, so I have wave coming in. Think of it as a little liquid or any material that you got, right? You take a little liquid, you pass this photon through, and you measure intensity afterwards, right? Very much like in your UV absorption cell that you did in your undergraduate lab, right? You have to stick a little UV cell with liquid inside, and then you pass light through. And here you just pass light through. You measure the start of the light, right, the incoming light, and then what the light intensity after it gets through. And usually, what do you see? Usually, in general, what do you see? If you plot, right, let me just plot, this is my I intensity after it passed through. Suppose I vary my photon energy, so I can vary my photon energy. What do you normally see? You will see initially starting at small photon energy, you will see discrete peak. This corresponding to absorption from one ground state to an excited neutral state, neutral to neutral transition, right? And then you would, suppose you have enough energy, right? When you have enough energy, you reach the ionic state part, right? Then you would have, suddenly you would have a rise in your absorption coefficient. But due to ionization, due to the fact that you pass that ionization. And then you would have a solder like this coming down, an edge, so-called edge. And then you will have excited state. You will also have a little excited state until you reach a second ionization edge, and then so forth, like this. Okay, so before the ionization edge, you always have sort of excited state, excited ionic state before. So these edges corresponding to ionization of your molecule, these discrete state corresponding to state. This one, for example, before the first ionization is the neutral to neutral transition. This is from excited state transition and so forth, like this. Okay, so that's generally what you see. Now, when you do UV absorption spectroscopy in the lab, we are way down here. We will not be able to reach because the little neon lamp that you use are very small in energy. They are typically less than 10 electron volt. They would not be able to reach your ionization edge. So all you're seeing is just a big peak, right? And that corresponds to electronic transition. One ground state transition to an excited electronic state transition. What we are talking about here is that we are talking about an ionization edge. We have enough photon energy, we go through reach this edge. So you see jump through an edge like this. And on top of these edges, what people found is that there's a lot of feature, right? If you look carefully, there's all these little tiny little peaks. They're usually less than 5%, right? You have to look really carefully. 5% of this intensity that you see, right? They're a very tiny effect. And then you have, if you look even more carefully, you have all this little tiny wiggle that you see. And this little wiggle, this up and down wave-like phenomenon, they're less than 1%, even smaller, right? So you really have to look hard at this. This region is less than 5%. This little wiggle is less than 1%. So, but if you look there, you see it. You see this little wave-like phenomenon, and these are due to what we just talked about, interference effect. That you have this photoelectron wave affecting the absorption cross-section, causing this little wiggle that you see. Okay? And that's the general XRF phenomenon. Now, to do this, to do XRF, you need, you can imagine, right? What am I plotting here? I'm plotting intensity, my absorption coefficient, as a function of photon energy, right? As a function of photon energy. Now, normally, you cannot, unlike the electron, which you can tune any energy you want, photon is a lot tougher because you can only have one wavelength at a time, right? With your light bulb and your resonant light, you know, neon light and so forth, you only have one energy, one photon energy at a time. So it's very difficult to continually change your photon energy. This is not so easy to do. If you just use a bunch of light bulb with different photon energy, like red light or yellow light, right? They would have different energy. Different neon light, for example, you can sort of do this. Different lamp, people call it lamp, to do this is very difficult to do. But in the late 60s, people starting to use something called a synchrotron. And what they found is that radiation coming out from the synchrotron is continuously tunable. You could actually continuously tune the wavelength of the photon you have. So you have and then you can do this experiment. So XRF actually occurred in the mid-70s. People started to discover, because that's the advent of the synchrotron radiation research. This new tool coming online, and people starting to figure out maybe we can use this to see this interference phenomenon. So this is a classic representation drawn to scale. You have a huge storage ring with your serrated electron. I'll talk a little bit more about this. And then the photon comes in, and then you have some sort of optics. And the optics capture this photon, focus it, and then onto your sample. So exactly like this. You have photon in, photon out. You stick your sample in the middle, and then you have some electronic to measure the intensity before and after, and you measure transmission. Okay? So this is historic. This diagram is historic. It's done by people at Stanford. Stanford, I forgot what P stands for. They have a sphere, well, the acronym stands for something. It stands for, forgot what P stands for. E stands for electron acceleration rate. Okay, so I think stands for photon electron acceleration rate. Okay, so it's a huge storage facility. I work there and work for life, so I know about these things. So here you have a photon, and what do you get from this, right? The photon X-ray absorption spectroscopy. Essentially, you're doing X-ray absorption spectroscopy instead of UV absorption spectroscopy as you've done in your lab, right? We can excite this photon into different energy regime, and I'm running out of time. I'm going to come back and talk to you about what are these wiggles, right? This chi structure that you see. There's a lot of information contained in this wiggle. Some simple mathematics, if you use a little bit of mathematics, you can fish out the information content of these chi curve, what people call chi curve. So I'll do that next day, and I'll try to finish off this part. So next